Hello, I'm Andre Rustino, Managing Director of the ISA100 Wireless Compliance Institute, also known as WCI. Welcome to the second in our series of technical seminars. Generally, these seminars are designed to address frequently asked technical questions about the ISA100 standard. And today we're going to talk about how ISA100.11a devices integrate with host applications. The ISA100.11a standard is the first standard approved in the ISA100 family of standards. .11a was designed specifically for the process industry. There are other future additions to the ISA100 family of standards, including things like factory automation, which is discrete manufacturing, and backhaul. So a lot of people ask about the application side of ISA100.11a as it was published in September of 2009 and then revised in January of 2011. For example, they might ask, what does the ISA application look like? How can I access the data in an ISA application network? So presenting the webinar will be Jay Werb, Technical Director of the ISA100 Wireless Compliance Institute. Jay manages the Institute's compliance certification program and leads technical initiatives. He's also an ISA100 committee member and the editor of the data link layer. That's the mesh section of the ISA100.11a standard. So Jay, as an introduction, can you briefly describe the application framework for ISA100?
Sure, Andre. Thank you. I could do that. Well, my name is Jay Werb, and let's see if we can cover the entire application framework in just a few minutes. Then we can spend the rest of our time today going into more detail. This first diagram shows the ISA100 standard from an application point of view. The entire ISA100 communication stack is shown as a simple UDP connection. This connection provides a secure connection between the field device and the gateway. The ISA100 standard without any extensions is sometimes called the native application layer. The native application layer supports a basic level of services for a basic device. These native capabilities support reporting of analog data, such as temperature, binary data, such as switches, and blocks of data, such as waveforms. Wireless communication services transmit this data to a gateway or some other remote location. Two types of services are mentioned on this slide, publication and alerts. Roughly speaking, publication is when a gateway configures a device to transmit data periodically, such as every 30 seconds. Alerts are when a device is configured to look for trigger points and send a message whenever exceptions occur. Now, these native functions, written right into the standard, provide everything that is needed to provide the user with a basic level of functionality. For more sophisticated applications, the Wireless Compliance Institute has defined some extensions to the standard that we will summarize on the next few slides. Okay, on the upper right of this diagram, we show a WCI Gateway Interface. In actual systems, you will find multiple gateway options. There will be gateways to Modbus, gateways to OPC, and gateways to FTT, for example. You will doubtless see other types of gateways as well. WCI recognizes that this diversity increases user choice, but we also decided that the marketplace needs a single gateway interface that covers the very basics. More sophisticated gateways can build on that base. WCI calls this baseline gateway the General Client Interface, and that is shown in this picture. Okay, on the upper left of this diagram, we show some WCI extensions to the ISA100 standards. These extensions include some codes that link the device to its certification. They include some diagnostics, as recommended by NAMER NE107. They include some basic data modeling, especially related to alarm. And they include some profiles, starting with temperature and pressure, and with more to come. To complete the picture, WCI has adopted device description files based on conventions established by Citation Fieldbus. Device descriptions are files that describe the capabilities and data structure of devices. We will discuss that in more detail later. Okay, so to summarize, we have 1, a stack that reliably and securely communicates application data between a device application and a gateway. 2, a native application layer that can be used to cover basic applications. 3, a general client interface that the host applications can communicate with devices on the network. 4, WCI extensions to improve the user experience. And 5, device descriptions.
So this pretty much lines up with what you'll normally see in the wired field bus world, Jay. But then what's the basic difference between wired and wireless?
Well, Andre, if the network is designed correctly, the wireless aspect should be well segregated from the end-user application. In this diagram, end-user application on the upper right shouldn't need to deal directly with wireless. I'll show that with a few diagrams. Okay, we will start by looking at a network diagram that is copied exactly from the ISA100 standard. On the left, we have a number of wireless devices meshed together. In the middle, we have an infrastructure feeding data through a gateway. And on the right, we have a plant network that consumes data through the gateway. Normally, the only thing that the user sees is on the control system on the right, but the standard is mostly focused on the interactions on the left side of this diagram. This presentation basically describes how these two worlds are integrated. Okay, on this slide, we take another view of exactly the same type of network, but from more of an application point of view. The previous slide focused on what the network looks like physically. In this picture, the network is treated just as a magic cloud. That should be the actual user experience, a network that just works. In this diagram, field devices are shown as little upside-down lollipops at the bottom, connected to a network that feeds data to hosts through gateways. The system manager to the left side sets up the network but is not involved in the data flow. As we've discussed in a previous webinar, the system manager function in ISA100 is separated from the gateway function. The system manager on the left configures the network, but the actual user data flows to the gateway on the right. As shown here, user applications normally interact with gateways, not with the system manager. How can the host interpret data coming from the various devices? Following common practice in the process industry, a device's unique personality is provided through device descriptions. Device descriptions are consumed by the user of the data. They describe the capabilities and internal structure of devices at the bottom of the diagram to the host at the top of the diagram. With device descriptions, the host knows exactly which interactions each device supports.
So devices have a lot of variation from one product to another. So for example, a temperature sensor is very different from a pressure sensor, and also different from different temperature sensors might have different features from each other. So device descriptions enable the host system to make sense of this product diversity, as I understand it. What are some of the building blocks that make this possible?
We go to slide 10?
Yes, we've got slide 10.
Okay, it's not. Oh, there it goes. Okay. The wonders of the Internet. Now I see it. Okay, we'll start with an overview of the ISA100 stack using a diagram that we borrowed from the previous webinar. This diagram focuses on communication aspects of ISA100. ISA100 is built on the Internet Protocol as indicated by the UDP IP in the picture. This is exactly as standardized by the Internet gurus at the Internet Engineering Task Force, generally known as IETF. ISA100 adds end-to-end security above UDP and below the device application. The Internet protocol is well layered, so normally ISA100 application developers don't need to think much about security. The developer can just treat the whole stack and its security as a magic cloud that just works. That is possible because ISA100 application layer is well segregated from communication details. Below IP is a radio mesh with another layer of security that is designed to protect the integrity of radio communications. At the bottom of the diagram, physical packets flow back and forth across the airways. The result of this is shown at the top of the picture, where application data and client-server requests flow between 2 points. Typically, data flows between a field device and a gateway, but data might also flow between 2 field devices. The main point here is that application layer communication is several layers removed from radio communication. Yes, the communication is wireless, but those wireless aspects are not a direct concern of the application developer. The wireless aspects are all encapsulated at lower layers of the stack. Now in this slide, we simplify the stack view for the rest of this presentation. First, we represent the stack as a magic box, a UDP IP OSI stack with strong security assurances. The gateway interface and user applications exchange application messages. For the purpose of this diagram, the gateway is shown as generic. It might be a native ISA100 gateway, an OPC gateway, a Modbus gateway, an FTT gateway, or something else. The communication between field device and the gateway is the same regardless. Second, we abstract communications using the word service contracts. What exactly is a service contract? So far, we haven't discussed quality of service, which is an essential aspect of any communication technology. In the ISA100 standard, quality of service is established through a service contract. We could spend this whole webinar just talking about service contracts, and maybe we will someday. But today, I'd like to just cover the very basics. Before an application starts transmitting data, it asks the network for permission. That permission is called the service contract. For example, suppose the application is configured to publish data every 5 seconds. Before starting this publication, the application needs to negotiate with the network to set up a service contract, which is the ISA100 mechanism for reserving the communication capacity. Contracts are expressed in terms of application requirements. For example, an application might request a contract to report data every 5 seconds. When the contract is granted, the application knows it can publish every 5 seconds. But the application layer does not know how the network is actually handling the 5-second publication. The application only knows that it has permission to publish data every 5 seconds. The service contract approach preserves layer independence and makes it much easier to add new radios to ISA100 in the future. Service contracts also make life much simpler for the application developer today. The stack handles TDMA, CSMA, and similar considerations completely transparently. Anyway, this very simple diagram represents the entire ISA100.11a stack as a turquoise square with security. The magic stack somehow provides a level of service defined by service contracts. The application layer has no idea if the network is using an 802.15.4 radio, a Wi-Fi radio, Ethernet, infrared, or smoke signals over IP. It's all separated to the stack.
Okay, I get it. So we're looking at a summary of how applications interact with the ISA100 network. Can you build on this picture for us, beginning with the gateway to show it how it all comes together with the end user application on the host?
Okay, sure. Now, this picture shows the ISA100 standard as it's written. And in the ISA100 standard, data is generally shown as falling between a field device and a gateway. But of course, the gateway isn't the final destination. Technically, the ISA100 network stops at the ISA100 gateway. The gateway then translates the data into another format and sends the data to an end-user application. We will show that in the next slide. In this diagram, we have the gateway function in the upper right. We already discussed this before. There are a lot of different gateway standards, such as OPC, Modbus, and FTT. As a starting point, WCI has standardized a basic level of gateways that can be used alone or can be used as a building block for other types of gateways. So here we show a general client interface providing a translation between an ISA100.11a gateway and an end-user application. The general client interface is the WCI specification. ISA100 itself includes a lot of material about gateways, but that information takes the form of general recommendations. WCI has built upon these recommendations into a specification of exactly how the interface shall operate. We expect ISA100 system suppliers to support this interface so that an end-user application can write one application that will talk to any gateway. Okay, now we will show how applications are organized on the device side of ISA100. We will start with the generic application services that are provided by the ISA100 standard, which together provide a baseline of useful capabilities. We will start by describing those basic capabilities. These capabilities are called an ISA100.11a application in this diagram. These simple but powerful functions are exactly specified in the ISA100.11a standard.
Jay, it might make sense to just start with the approach that ISA100.11a uses to publish process data from a field device to a gateway, which is really the most fundamental function of an ISA100.11a network anyways.
Okay. Good. I just happen to have this slide to discuss that. This picture shows a publication. Publication is one very important concept in the ISA100 application layer. Normally, most of the actual network traffic will be publications. What exactly is publication in ISA100? Publication is the periodic reporting of some information across the ISA100 network. For example, if a sensor is configured to transmit data every 5 seconds, we say that the information is published periodically every 5 seconds. In ISA100, publication is normally accomplished through a concentrator object, as shown in this diagram. A concentrator object assembles data from various types of data in the device and packages that data together, or concentrates the data. Then, the concentrator object publishes that data to another location on the network. Typically, a gateway is shown here. Not shown in this diagram, there is a symmetrical object on the receive side called the dispersion object. The gateway in this picture uses a dispersion object to disassemble the publication whenever it is received. The concentrator object is very versatile and can publish any data in the device. But most of the time, a concentrator object will publish two types of data, analog input objects and binary input objects. An analog input is a 32-bit floating point number, such as temperature or pressure, plus a status byte. Binary input is an on-off status plus a status byte, such as a contact. These basic objects, analog input and binary input, are fully defined by the ISA100 standard. Analog inputs in ISA100 are sometimes compared to 4 to 20 milliamp, very simple, but also very useful. As an example, this diagram shows a concentrator object that publishes temperature as an analog input, pressure as an analog input, and a contact as a binary input. These readings are packaged together by the concentrator object and published periodically. This publication is received by a dispersion object in the gateway, and from there it is forwarded to one or more hosts. The ISA100 standard describes all of this in exact detail. Okay, this picture looks similar to the previous slide, but it shows a completely different type of reporting called alarms. Alarms are also fully specified by the ISA100 standard. When alarms are used, a host configures some trigger points associated with an analog input object. For example, a certain pressure level might trigger an alarm. When the value crosses the threshold, the device goes into an alarm condition and immediately sends an alarm message. When the value crosses the threshold in the opposite direction, the alarm clears and we see another message. For example, imagine an application that needs to report exceptions within 10 seconds. If we use only the publication approach, we need to transmit a message every 10 seconds, even when the data is almost exactly the same. Why should we waste battery and network resources just to tell the host that nothing interesting is happening? In many applications, alarms can make these extra reports completely unnecessary. Instead, the user might configure devices to report once per minute or something like that. But at the same time, the user can also configure the device to report alarms immediately, as quickly as the network can transmit them. If the network is correctly designed, alarm reporting can be surprisingly quick. Anyway, when you put these two approaches together, periodic publication and exception-based alarming, the result is an optimal balance between energy, data freshness, and fast alarms. The combination is much more efficient and scalable than using either approach alone. Publications and alarms are fully specified by the ISA100 standard as part of the generic application layer. So to review, here we go. We have a data publication with data periodically published through the gateway using a concentrator object. Normally, once the network is up and running, most of the network capacity will be used by this type of reporting. Then we have alarms. Between publications, if trigger points are crossed, an exception is immediately reported through the gateway. In most applications, there shouldn't be a lot of exceptions, so alarms shouldn't use a lot of energy or network capacity. But the network does need to be properly designed so that exceptions propagate quickly and reliably.
So you've just been describing the capabilities that are part of the ISA100 standard that are within the device's application process, which is the generic application process shown in the red dotted line. Publications and alarms are fundamental, but there's also some other important features in the standard. Can you take a few minutes to look at them as well?
Sure. There we go. Now, the yellow box on the left will show the major services offered by the ISA100 user application process. We start with some services provided by the application layer. This is where you will find general-purpose ISA100 application services such as read, write, publish, subscribe, and execute. Standard data types are defined at this level. An alerting object reports alarms and events. Service contracts discussed earlier are negotiated using these services. Moving up to the next point, we come to what's called unified field objects in the ISA100 standard. For example, an analog input object is defined in the standard. The temperature sensor in ISA100 would report its data through an analog input object containing a floating point number that represents the degrees Celsius or some other unit. This object represents the state of an analog input and includes a scaled floating point number, a status, and a few other basics. The 32-bit data uses exactly the same units as Foundation Field Bus. For example, unit code 1001 is degrees Celsius in both Foundation Field Bus and ISA100. About 700 different units are defined, allowing for a lot of flexibility. For example, unit code 1634 is barrels of US beer per second in both ISA100 and in Foundation Field Bus. The next thing shown is the upload-download object. The upload-download object supports transmission of large blocks of data, kilobytes or even megabytes long. It has two major purposes. Every ISA100 device can receive stack downloads through the upload-download object. That means every ISA100 device is required to support stack upgrades over the air in a way that is precisely defined by the standard. Upload-download can also send waveforms in the opposite direction in specialized ISA100 devices. For example, vibration sensors or corrosion sensors can use the upload-download object to transmit waveforms in an interoperable way that is defined by the standard. So, that was a quick tour of the ISA100 application layer, which is sometimes called the native application layer. It provides some generic services that can be used to report a wide variety of data in a very flexible way.
Thanks, Jay. So what we've seen here is just a quick summary of the ISA100.11a application layer. I guess the main point here is that the ISA100.11a standard provides a complete framework for reporting process data, roughly corresponding to the 4020 milliamp level of capability. An important aspect of the ISA100.11a application layer is that it's object-oriented and very extensible. So these basic capabilities can be extended by a supplier or by additional specifications. Although you can build a perfectly functional ISA100.11a device without any extensions. WCI has developed some extensions, and these extensions are targeted at the process industry. Remember that the extensions don't change anything in the ISA100.11a standard, and they do provide additional capabilities to improve the user experience. Maybe you can take a couple minutes, Jay, and talk about some of these extensions.
There we go. Next slide, please. There we go. Okay. The first set of extensions relates to general device information. This includes the device's manufacturer ID and tag. It also provides information about the device's certification. In addition, WCI extended ISA100 to cover device diagnostics, following the guidelines provided by NAMR and NE 107. For example, if there is an electrical fault in the device, that is reported as recommended by NAMR 107. This is a good example of what WCI calls a blue specification added to ISA100. ISA100 refers to NAMR 107, but does not describe exactly how it is integrated into the ISA100 object model. WCI has written a specification to connect these two standards in a way that will be consistent across suppliers. The next set of extensions relates to the standard ISA100 input objects. The baseline ISA100 standard covers the process data that is reported to the device, and also a mechanism for reporting alerts based on trigger values. WCI has extended this to cover some specific capabilities that are useful for many types of devices in the process business. This includes filtering and alarms with hysteresis. It also adds a simulation capability so that WCI can effectively test and certify the devices. Continuing down the list, WCI is building on ISA100 objects to define a set of profiles for specific types of devices. WCI wrote specifications for temperature and pressure profiles in 2010, and we are working on a positioner profile now. These profiles include things that are specific to the type of device. For example, the temperature profile includes thermoresistance compensation, which of course is very specific to temperature devices. These aren't exactly glue specifications because they don't specifically refer to another standard. However, when we write these profiles, we try to follow general conventions already established by other standards. These WCI profiles are modeled on similar foundation field bus specifications. We make adjustments as needed to account for the ISA100 object model, and we somewhat simplify things for wireless. But still, the general goal is that WCI profiles will be similar to foundation field bus, so that integration is straightforward for systems that already integrate with foundation field bus.
Okay. Now that we're on the subject of Foundation Field Bus, let's talk about device descriptions. I know fundamentally that device descriptions are files that describe the capabilities and data structures of devices, but can you kind of expand on that a little bit more?
Sure. Let's quickly review the purpose of device descriptions. They provide an extended description of each application object in the device, which might include proprietary objects that are not covered by the standard. For example, there might be an LCD display on the device that is not standardized. A device description can be used to give the user access to that proprietary display. Generally speaking, DDs enable users to understand the meaning of a device's data and to access all of its functions. DDs enable the system to be configured without having the device online. And generally, a DD opens up host-device communication without custom programming, even if the device has custom features. All of this should be very familiar territory in the process business, and there are already standards to cover this. There is no reason for WCI to reinvent the wheel, and this is a good opportunity for another set of WCI glue specifications. The result is that Foundation Field Bus device descriptions can be used with ISA100. You can already see this working in ISA100 products, and DDs are already simplifying host integration. Okay, this slide shows one simple example of how a Foundation Field Bus device description can be applied to an ISA100 device. The general idea is that a user interface is automatically generated based on material provided in the DD file. For example, there is a selection list on the user interface, and the available selections are determined by the device description. My main point is that this will look very familiar to people who are well-versed in Foundation Field Bus. So now, as a conclusion, let's review the overall picture. Good. Inside of the field device, to the lower left, there is an ISA100 application layer that provides services such as read, write, alarms, and publications. It is typically configured to publish sensor data periodically and to publish exceptions as alarms. The data can be input or output objects in natural units such as degrees Celsius. The application layer is also capable of moving large blocks of data such as firmware updates to the device or waveforms from the device. The application layer is object-based and very extensible, and WCI extensions are shown to the upper left. WCI has added extensions to cover NAMR 107 diagnostics, temperature sensors, and pressure sensors. A positioner profile will be ready soon. These and other device extensions can be exposed to the host using Foundation Field Bus device descriptions. Data at the gateway is exposed to the control network through a general client interface.
Okay. Well, Jay, I appreciate all the work in putting together a summary of the ISA100 application integration layer. And I encourage participants to visit the ISA100 WCI website for dates and times of upcoming webinars on the ISA100.11a technology and any other current happenings, new device registrations, that sort of thing. So again, thank you for your time today.